All right, and welcome to the next part of my little series on how to get load cells working with Hopper on microcontrollers, just basically Hopper programming tutorials. In this part, we're going to implement a reset button and show you how to debounce it with two resistors and a capacitor. And we're going to calibrate our scale using a known weight. Okay. I did gloss over something in the previous section when it wasn't working and I managed to get it to work. And the bit I glossed over was overclocking the microcontroller, in other words, running the microcontroller twice as fast as its default speed. And there is actually a comment about that. I think there's a comment about that in the read function or the shift in function. Yeah, this comment here describes why I do that. And it's because Hopper is an interpreted language, not a compiled language. So the amount of it doesn't need any delays between these clock pulses out to the HX711. In fact, it delays too long. And with most serial interfaces that you can bit bang, in other words, manually do the serial interfacing, with most of the interfaces like that, it doesn't matter if you have a slow clock. But with the HX11, it actually has a maximum high time for setting the clock pin high. So a maximum period for which you can set the clock pin high. So here we are setting the clock pin high to true and setting it to false, to a clock cycle to shift in the data. So the maximum length of this period is actually 50 microseconds. And that's microseconds, not milliseconds. Which means that in the Hopper, this code needs to be really tight. I just store the data value and then flip the clock again. Because the load time, there's no maximum. So the load time when it goes around this loop again to the top doesn't matter. So in that long period, I do all the rest of the code. So in the high period, I do as little as possible. And if I overclock it, it works more reliably. So it says, I said here, it appears to be fast enough at 133, even in the debugger, which is the default speed on a Raspberry Pi Pico. But, when I was writing my code live on my video, it wasn't working. So my solution was to just double the speed of the microcontroller. And I haven't seen anything adverse happen because of that. Anyway, let's move on to the reset. So we want to be able to call reset on demand, like when you press a button, right? So how do we do that in Hopper? Let's have a look. So Hopper has something called events. So you can make a button event. And so we can make this reset. And an event is also known as an interrupt. So you can make a button interrupt service routine, ISR. And you're going to put it, it's going to, well, are we going to do anything with the pin? Oh, it's always going to send me the pin. So the event's always going to send me the pin, and it's going to send me the pin status, which is, what was the pin doing? Was it going high? Was it going low? Was it, is it currently high, currently low? So when you hook up an event, you can do it based on different pin action. And all we're going to do, I can't pass that around. So I'm going to have to make that global again, which, like I said, is not exactly ideal in terms of programming style. So I'm just going to say our scale only works with one cell. So now I have my cell. So that means that I can call inside here, I can call reset cell like that. So when my button interrupt service routine is triggered, it's going to call reset, and it's going to reset out our tar value. Right, now we need to set up our ISR. So how does that look? In Hopper, there's already defined something called a pin delegate, a pin ISR delegate. So we can do that before we initialize here. We can say pin ISR delegate and button delegate and we just say what, it's a function pointer, so a delegate is a function pointer. So we want it to go to the button ISR, right? That's our delegate. And then what are we going to do with that? We need to configure it to do something with this board. We need to also make sure that the pin is set to be an input. So we've seen what we do with pin modes already, like when we were setting up our pins in here. Actually, when we're doing the blink program. But so pin mode. So which pin are we going to use? I reckon we're going to use the next data pin along. So there's a ground pin in between, and then there's another data pin in there. So let's go have a look what that is. So that is GPIO 13. We're going to use the next. So skip the ground and put it onto 13, right? So let's do that. So we're going to use the next one along after the ground, like so. Yeah. Skip one hole. All right, back to the program. So now we know that that pin is going to be GP13. And we're going to set it to pin mode output, right? Pin mode option. Oh, input, because it's not an LED, it's a button. Input. I'm getting an input signal from it. And then if MCU, actually I can go to say attach to pin. So we can go see what that does. I just know it's called that. So attach to pin. So attach to pin returns a Boolean, and it returns, I think it returns true if successful. We can find out. And then these are its arguments. So it's going to take the pin, the delegate, and then a status. So the pin status is it rising? Is it falling? When it's low, when it's high, and that's why you pass the pin status to the delegate as well. So that's where it comes from, right? So control backspace, attach to pin. We want to attach it to this pin. We want it to call our delegate. And one more argument is, what was it? Switch back. So that was control tab to switch back. Pin status. So pin status, and we want to do it on rising. So we're going to hold this pin low, except for when you press the button, it's going to, no. We're going to hold the pin high, and then when you press the button, we're going to pull it to ground. When you release the button, it's going to rise. So it's when you release the button, it's going to trigger an event. And what we're going to do here is say, we're going to put an error message out, IO Reichlen fails to attach GP13, right? All right, so we can test this, we can build it. I'm going to plug the power into my board, and I'm going to put that, let's just make it high for now, we don't really care. Well, that's probably not a good idea, just to, short it to high, because you don't know if it's an input or an output. So, what can we do there? Let's just put it through the 10K resistor to high. So we're going to put, so let's put a 10K resistor to high there, and then put it to the 10K resistor like that. So we've got it pulled high, so it should never trigger like this. It should just, because it's never going to be rising, it's always just high from when the programmer goes. Okay, so now let's upload that program. And let's run it. Great. So we didn't fail out of there with an uninitialized pin. So far so good. Now let's go think about how we're going to do our circuit. So I'm not much of an electronics guy. I'm more of a software guy. So I use other people's electronics. So let's go have a look. So Elliot has this really good article on debouncing buttons and why you need to do it. So basically, if you have an electrical button and you press it, there's like sparking that happens inside the button, and you get multiple clicks for every click. And I'll put a link to this in the description as to why you need to debounce a button. So you want to debounce a button so you get only one event that gets fired. Otherwise, we'd get multiple tar events fired for every button press we hit. And he's got sort of two levels of debouncing, and the one involves using an IC as well. But I find that his first circuit is perfectly adequate. So we've already put in our 10K resistor here, and put that straight to the pin that goes to the microcontroller. So he's got an RC circuit here, and he explains the RC circuit. But basically, if you multiply the R and C values together, you get the time delay of the time window for which it'll have one pulse. And he's got his values here, 1K and 0.1 microfarads or 100 nanofarads. It gives you 0.001 seconds, which is short enough to get rid of the electrical sparking when you press one of these little buttons. All right, so we're going to pull it to ground through a 1K resistor, and we're going to have a 0.1 microfarad resistor also going to ground. So let's get back to our circuit. So let's pop in our button. Oops. It's quite fiddly to do this with the microphone. I'm going to get rid of the microphone. There's my button in on one side. And, I don't want the button in on that one. I actually want a 1K resistor. Make it a little bit narrow like that. 1K resistor there. Is it really going to work? Okay, let's pull that out again. There we go. So that's going to be the one that goes to my device, and then I'm going to want my 0.1 microfarad in there. So I'm just going to make it easier to lay out by just putting two lines to ground. So that one's to ground for the one for the mic for the there. And then my button's going to connect the 1K to ground. So button's going to go into there. Because these buttons connect this way. So it's got actually two poles on it. But anyway. And then we're going to take the other side of the button to ground as well. So that should be my button debounced. So every time I press that button, it should cause the tar function to work. So let's see if it does. So let's switch back. There we go. And let's reload that. Load up the program. So it did the reset once, and if I press the button, it should reset it again. And it did. So there's a short delay. So press the button. So every time I press the button, you'll see a new reset here. So let me press the button, and then we get that. Yep. Maybe we can shorten this delay, and then it won't take so long to reset. Let's see if that works still with the in this loop. So make it 5 times as fast. Generating, okay, upload it again, and then F5 to run it. And there's so how long's our reset now? Yeah, it's a lot faster, and it's still resetting to a value we expect it to reset to. Right. Okay. Now next thing we're gonna do is calibrate, right? So this is close to 0, and you'll see what I mean by close to 0. You know, like when it's that smaller number. And to calibrate it, what I'm going to do is I'm going to use a known weight. So here we have a known weight, right? And I'm going to put the scale in a vertical position like that. And then the next thing I'll have to do is reset it for the vertical position, because you can see it's gone up to 7,000 now because it's weighing the hook. So now we're at 0 for the vertical position. And now we're going to lift our weight on it. Not very scientific, but it'll work. Okay, so we've lifted our weight, and let's call it, it keeps alternating, let's call it 356. 356,000 was the reading. So you can see why that's close to 0 when it's got, you know, two-digit numbers. So 360,000 was our number. All right, I just pulled up a calculator. So we had approximately, the reading was 360,000, and that reading was for a 1.5 kilogram gym weight. So 1.5 kilograms is 1,500 grams. So divide that reading by 1,500 grams, and we get the value of 240. So 240 is the number of units from our scale that equals 1 gram, right? So let's go have a look at how we're going to deal with that. So what we'll do is we'll come up with the constant, and we hope that calibration is probably always going to be true for this device. We're just going to assume it is. So constant, and it's a long value since the reading we're getting is a 32-bit long, and we're going to call this our gram factor, which is 240, right? And you know, calibrated using a gym weight, and that's just for clarity, that would be the number of grams per reading value from the HX711, right? Okay. Now, what can we do with that? We want to use that to convert between the readings we're getting and grams. So, and it also means we can ignore those small values, right? Because now, so that's the reading value, just to be clear. And oh, I'm in the reset. I don't want to be here. I want to be down here. The reading value. Here we go. That's the reading value. So now we can calculate in longs. We can calculate grams equals reading divided by gram factor. And now what I was saying is that we can ignore, if it's say less than 50 grams, we'll ignore it. So if grams is greater than 49 or greater than or equal to 50, then we can put the reading out like this, and we're going to put out grams. And now we can say it's actually a weight. Or a mass, because weight is mass times gravity. So the mass is grams. There we go. So let's see if this works for us. And F5, successfully uploaded. Okay, run it. Running in the debugger. So now, if we hold it vertically and we press the tar button, now we've calibrated it, and now we put our, if we can just pull on it a little bit, we get weights. So, but they'll never be little. And you see, it's not running those empty like -1s anymore. So now we can pick up our 1.5 kilo weight, and it's pretty close to 1.5 kilos. Obviously, I could calibrate it better, or it's just my setup's not great either. But it's pretty good, pretty close to 1.5. So we've calibrated our scale. I can do a little bit more in this video to show how we can display kilograms, for example, just for fun. So let's get out of there. So let's make ourselves a display kg, and we're going to pass in grams, right? So we've made ourselves a new function here, display kg. And how are we going to do that? So so we know it's a long still, so long grams, and we're going to have a second grams in here, so let's make this total grams, right? And then what we're going to do is we're going to say kilograms is going to be total grams divided by 1,000. And because they're longs, not floats, that's just going to round it off to the nearest kilogram. But then we can get the remainder by going, we could have done mod to get the remainder, but we can also do it by just going the actual grams is going to be that total grams minus kilograms times 1,000. So that's our fractional grams. And now we can say the measured weight is going to be IO dot right line. We measured, and we can say kg to string, and we can pop in a decimal, and then we can do grams to string, right? But grams is could be 2 digits long or 1 digit long, and we want it to always be 3 digits long. So you can do that by taking this string, putting it in an expression like that, and then you can say pad the left side of it with zeros to a width of 3, like that. There we go. And that should do it. Let's try this. I didn't like 2 strings. We want 2 string there. Typo. Okay. Not left pad. Keep making typos. And F5 to load that. And then let's run it. And now we need to pick our scale up again. And I've got our scale ready. And we're going to hit our calibrate button, our tar button. There we go. We've calibrated for the weight of that. And then if we pick up our weight, why is it not giving me what I thought it should? Oh, because it is. It's 1.5 kilos. I just forgot to put kg in there. So that was my mistake. So if I go back out of there, I just forgot to put a unit in here. So that confused me. F7. Anyway, there you go. We've got a calibrated scale with a reset button, which is an improvement on what we had last time. Let's run it again. And we've got to reset to measure the weight so that the weight of the hook doesn't mess up our reading. And then we can pick up our 1.5 kilo weight. And it is close enough to 1.5 kilos for government work. Bearing in mind it's off by 10 grams, 20 grams. It's not bad. And this is a 10 kg load cell. So if you wanted to weigh something small, you'd use a more accurate load cell for smaller weights, like a 1 kg load cell. Whereas this should be close. This should get the kilos right, and that's close enough for me. Or certainly close enough for our demo. Anyhow, thank you for watching. I reckon the next part in this series is going to be about how we can make this work on displays. So how we can display the weight on our device instead of through the serial port here. Thank you very much for watching.